I will start with some motivation and some context before getting to specific results. So, in most of the talk, X will be a compact metrizable space. Okay, so associated to any such space, we can look at complex vector bundles. Okay, isomorphism classes of complex vector bundles, and there is a natural operation, tensor product. Okay, so tensor product of line bundles. Well, it turns out that this is an abelian group, and what is the inverse of a line bundle? Turns out that it's complex conjugate. So this is one. Right, so you see, to each space there is a way of attaching an abelian group, right, and in a functorial way. So it is quite natural to ask, can we integrate this abelian group within a larger theory? For instance, is this the first group in some cohomology theory? Okay, and of course that's the case, and that has been known for long. Right, so line bundles are in relations with principal bundles where the fiber is the circle. So you know that we can identify this group actually like that. So this group is isomorphic to its known to the second homology C, and then the right, this isomorphism is given by, for instance, the first chain class. So, and the operation here is the addition. So yes, this is the first group, the zero group in a cohomology theory, which starts, which corresponds precisely to Eilenberg-Maylength, Eilenberg homology, right? And right. And one way, there are many ways of viewing this. Okay, and when doing this, I ask, okay, the next group is H3XC. What would be a geometric realization of this group? Right, so for H2XZ, we have isomorphism classes of line bundles. What about H3XZ? Of course, the homotopy theory, right, algebraic topology says that, oh, this is just homotopy classes from X to Eilenberg-Maylength space. Yes, but that's not it's a homotopy theory, theoretical realization. Okay, and then right, one of the results, implicit results of Dixmier-Douady was realized H3XZ as isomorphism classes of locally trivial bundles over X. So during the, my previous talk, I used the letter C for locally trivial continuous bundles, continuous fields. But now I want to insist to view them as bundles because they are locally trivial. So I use the letter B, B from bundles, right? With respect to the tensor product, and then they prove this as a matrix where this corresponds to X, Z. And if one has a bundle, then A, then the inverse is given by the opposite bundle, or the opposite system algebra. Okay. Maybe in these bijections, A goes to Dixmier-Douady class. Okay. So yeah, well, okay, what about H4XZ? So there are no known elegant descriptions. Yeah, so. All right. Now, along the same lines, we know that we have another abelian group associated canonical group, such as space. That's the K-theory. Okay? Where the operation is induced by addition of vector bundles, right? But we know that in fact this has more structure. It's a ring. Okay, it's a ring. It's a commutative ring. So we might look at the invertible elements in this ring. Okay, so these are the group of units in, okay, of the K-theory. And the operation is given by tensor products. Induced by tensor products of vector bundles. Okay, so it turns out that this is precisely correspond to classes of vector bundles of virtual rank plus minus 1. Alright, so I have a vector bundle of dimension n plus 1 minus a vector bundle of dimension n. Or the other way around. Okay, those are precisely the units here. If X is connected, otherwise this happens locally. Okay. And Graham Siegel, posed this question that you see, this is a natural functor. To each space, we associate an abelian group. Can this be integrated in a generalized homology theory, just like it happened here with vector bundles? See, here we have vector bundles of rank 1 after isomorphism. Here we have vector bundles of virtual rank 1. Can I integrate this? Okay. And so it gave an answer, right? So there is a generalized homology theory. And we denoted this by B. Okay, and I'll use a bit of algebraic topology jargon, so what he showed is that the PU, it's an infinite loop space, but here I have to discuss what is the structure, right? Of course, if I'm looking at this abelian group, it's integrated in K-theory. You have K0, K1. Okay, this would also be an infinite loop space, given by the both periodicity, but Siegel look at this where the operation is given by the tensor product. Okay, and it turns out he proved using the theory that he developed and also made the infinite. This is an infinite loop space. So there is a sequence of spaces such that the loop space on each is homotopic to the previous space. Okay, and so in this cohomology theory, the first group we use with X is this. Okay, now, of course, you can continuously U1x, but there was no bundle descriptions of the following group. You know, so. And one of the outcomes of this research that I did with Ulrich Pennig, we gave a realization of this. So maybe I'll emphasize this. So this is isomorphic to vector bundles, not vector bundles, isomorphism classes of locally trivial vector fields where the fiber is the Kunz algebra or infinity tensor the complex over X, and isomorphism classes of such bundles, and the operations is the tensor product. Now, if you insist here to have you have a subgroup here where you take virtual rank 1, they also form a group. You can take either orientable bundles of this sort or bundles where the fiber is the stabilization of the Jamsu algebra. That will give the theory for which dilutes this. Of course, just in this case, there is no known bundlerization of BU2. So now let me go back to Dixmier-Douady. Okay, so I reviewed the two basic results last time, but I'll mention them briefly again. Okay, so the local triviality, right, is given by, is detected completely by the fail conditions. So this is the dimension of the space is finite dimensional. So if you have a field of complex of a finite dimensional space, if you can find local projections of constant rank 1, that's precisely the necessary sufficient condition for local triviality, okay? And then 2, the locally trivial fields is fiber compacts. Isomorphism classes form a group under the tensor product. Operation induced by the tensor product, and this is isomorphic C. Okay, and 3, so this is a result of Serre. It appears, so this is well known now, it appeared originally in the Bourbaki seminar series of talk by Grothendieck on Azumaya algebras. Okay, and it shows that the torsion subgroup A3 fits well this picture, namely all elements there occur as Dixmier-Douady classes associated of a continuous field of matrices. So I would say that a continuous field of compacts plus its torsion, so n times 0, if and only if there is a field B of matrices, and I'm defining here, matrices of order m and k, or some k, over x, and it's the same m there, such that A is isomorphic to B tensor the compacts. Right, so you have a field of matrices, and if I tensor with the compacts, I get a field of compacts. Okay? Now, in that way, we hit precisely all torsions elements of H3. Okay, and this is a non-trivial homotopy theory argument. So, of course, since then, this was 58, since then the theory has evolved. And it's no longer tricky. But initially, was a big asset to the argument. All right. Now, the goal is right, is generalized. Okay, so now, what is the natural framework for generalizations? Okay, so for any, if we fix a topological group, right? One can consider this general question of how do we classify isomorphic classes of principal bundles, principal G bundles. Okay, and so the answer is, that's the homotopy theory questions. It's homotopy classes from X to the classifying space of G to BG, right? But is that computable? Is that part of a general theory? Okay, and if we want to insist, we want to have similar group operations where the operations is given by tensor product. So let's assume I have a sister algebra D and continuous fields with fiber D. If I take tensor products, then I get continuous fields with fibers D tensor D. I want to have an object of the same type. So I would ask that D tensor D is isomorphic to D. Okay, just like you have now the complex tensor, the complex isomorphic to the complex. All right. Now, but there might be many isomorphisms. Is there a canonical way or unique way up to homotopy to make that identification? That's a huge problem because there are certain rather subtle obstructions coming from homotopy theory. In fact, the so-called Samuel products. So this has been explained by Victor Nistor when he studied continuous fields of AF algebras. So even if you have an algebra D such that D tensor D is isomorphic to D, the corresponding this semi-group, the operations, it's not natural, does not commute with pullbacks. Okay, so you need D tensor D to be somewhat canonical isomorphic to D, or in a very strong way. Okay, so, and it turns out that a suitable concept is the strongly self-resolving system. Okay, so here I will just say that D is strongly self-absorbing if and only if D tensor D is isomorphic to D and plus some stronger conditions. For instance, okay, plus conditions. Okay, I'll give a precise definition. So, if D is a Kirchberg algebra, so if you're linking it right? This extra condition, I have, this is the result. Just assume that the second fundamental group of the automorphism group of D is 0. So what I'm saying is that if you have a Kirchberg algebra such that this phi 2 is 0 and D tensor D is isomorphic to D, then it follows that the algebra is strongly self-absorbing. Okay, you might think, okay, might ask, okay, what if this group is contractible? That's even stronger condition. Right, so if it's contractible, it means that up to homotopy, you know, there's a unique way, very coherent, unique way of identifying D. All right, so in what sense, what is the setup of the generalization? In fact, we want to look at isomorphism classes of bundles with fibers D tensor K. So this is going to be a unital strongly self-absorbing. Okay, with respect to the conservation. Okay, and this Dixmier-Douady case would correspond to the strongly self-absorbing D per C. And of course, C tensor C is isomorphic to C, and the automorphism of C, right, that it's contracted at one point. So, now, let me, instead of giving the precise definition of strongly self-absorbing theorem, algebra, I'll give a result. So, and then examples. And this theorem, you know, can be, it's a characterization of strongly self-absorbing algebra, but it's equivalent to the definition. Okay, so this is characterization of strongly self-absorbing algebras. So they were introduced by Thomson and Miller, and we have shown that the following. So let D be a separate resistor algebra. So then D is strongly self-absorbing. If and only if. Okay, so the map L from D. Okay, so this is a unital system algebra from D tensor D. This left inclusion L of D equals D tensor 1 is strongly, I'll just say, unitarily homotopy equivalent, unitarily homotopic to some isomorphism gamma from the tensor. okay? And more explicitly, so there is a continuous map on the open interval with various unitaries such that it starts at 1 and limit as t goes to 1 ut L of t ut star is gamma, where gamma is isomorphism. So you see, what is asked, there is a continuous, an infinite path of unitaries starting at 1, which conjugate asymptotically the inclusion, right? So this inclusion is certainly not subjective to some isomorphism. The original definition of Thoms and Winter was exactly like this, but they asked for a discrete sequence of unitaries. Okay, and if one wants to do calculations and analyze continuous fields, one really needs these stronger versions. And in fact, this was a question asked by Eberhard Kirchberg in his papers from the previous other seminar. There was this open question. On the unit interval, you have a continuous field with fiber isomorphic to D. So in the middle looks D tensor D, and at one hand you have functions which takes values in D tensor 1, at the other hand you have functions take value in 1 tensor D. Is this the trivial field? Okay, so that was the question. And with Wilhelm we found these equivalent stronger characterizations, and that also solves the problem that Kirchberg asked. But let me give examples first. So this list of examples are all the examples that satisfies the universal coefficient. Yeah. Okay, but before I give this example, I should mention that if an algebra is strongly self-absorbing, it means that it is nuclear, simple. This goes back to work of Efros and Rosenberg, and it is either a Kirchberg algebra, okay, so it's purely infinite, or otherwise there is this dichotomy, or it is stably finite with unit trace. So what are all examples of known examples? Okay, so the complex numbers, right, as I mentioned. Then, so really, it's infinite dimensional cousin, the so-called Jiangsu algebra. Okay. Then we have its infinite version, which is co-infinity. Okay. Then we have the infinite UHF algebra, the UHF algebras of infinite type. So maybe I'll put M sub P infinity, where P it's a set of tracks. So if this is the Carr algebra, if P consists just of 2, and maybe if I take all possible primes, this is the universal UHF algebras. Tensor product of all matrices, right? And now what happens if I tensor anything here with infinity? Let's see some examples. And then we have output. So really, there are only C, this, and those are, implicitly reduced, by this operation, localization of the prime. So it is just the C-star algebra analog of localizing the prime. And if one assumes that a Scobie absorbing algebra satisfies the universal coefficient theorem, then due to the recent results in classification theory, all of these are this is the complete list. And this goes under tensor products and so on. Okay. So now another result we have having this, right? Maybe mention this as a theorem. So now, so D, so right, D here is from such a sort. Okay. Then any unit of field with fiber D over a space X, which is five-dimensional, is actually trivial. So A is isomorphic to COX. Very simple. This is false if X is infinite dimensional. Okay, and right, so the role of this in the general theory, it's similar to, like some sense the statement, which if you have a continuous field over a space X where the fiber is the complex numbers, that's COX. Okay, so that holds, of course, without assuming that X is five-dimensional. All right, so now in pursuing the generalization, so now we need several things. One, is there a fail condition for local triviality? So I discussed last time what is the fail condition for for continuous field of Kirchberg algebras. And in fact, for any abstract algebra with a KK theoretic condition. All right, but in this case, we'll simplify. This will simplify. Okay, so, and maybe, I'll mention another result just without too many comments. What it happens if you look at KK of A tensor B for any separable system algebra. Yeah, it's separable. Turns out that this is isomorphic to K0 of A tensor B. And isomorphism, you just restrict this, this is induced by restricting K theory to a copy of C, which sits here as a multiple of identity. Now, Fell's condition involved KK theory in general, and now due to this, Fell condition will simplify. Okay, so So what is the analog of rank 1 projection? Okay, so if I have K, right, so the fair condition involves rank 1 projections. I have local rank 1 projections, right? But if the fiber is D tensor K, okay, so what is the analog there? Okay, so now, one of the many pleasant properties of strongly self-absorbing system algebra is that K0 of T is commutative. D tensor P is isomorphic to D. Very unique property. So this is a ring, right? Now, in this ring, we can look at the invertible elements, the units of the ring. Okay? And this is what it goes there. Indeed, what are the rank 1 projections, right? I'm looking at K. When I write the compacts, right? When I write the compacts, right? This corresponds to the case B equals C. Right? And then K0 of the compacts, right? Which is it's K0 of C. Maybe I should write the compacts, right? So the compacts, I want to write them as C tensor of the compacts. So we see the analogy. What are the invertible elements here, right? This is Z. K0 of K is Z. And what are the units of Z? Plus minus 1. So this is what it means rank 1. And it turns out, moreover, if the class of a projection is a unit, if and only if you compress D tensor K by the projection, this is a sister algebra isomorphic to D. Right, so if you compress the compacts by a projection, you get C, a complex number, if and only if the projection has rank 1. So maybe I should mention, for instance, what if I take the car algebra, right? Then the K-theory and the adic numbers, and what are the units of this ring? And this is a ring. These are powers of 2. This up. And if I take the universal algebra, K theory is Q, and the units are the non-zero rational numbers. All right, and the result here, so is Pennig again. So now the remaining of the results will be adjunct to Pennig. So says that if the dimension of X is finite dimensional, and A it's a separable continuous field over X, its fibers D tensor K. D is a strongly self-absorbing algebra, so we don't assume UCT or anything. Then A is locally trivial, if and only if it satisfies third condition. So if and only if we have the third condition. So meaning, what does it mean is that there exist, there exist local projections P, right? Let me write in A of V. So A is a field over X. Around each point X, I can find a close neighborhood, such that if I restrict the field there, that's A of V. I find there an idempotent, a projection, such that if I'm looking at its values in the fiber, I get a unit. Right, so it's precisely rank 1 in this sense. And strongly self-absorbing algebras have such good properties that, in fact, we can do this with positive K-theory elements. We don't have to work with. Okay. All right. And maybe I should make one comment here. So you see, let me explain, or have explained this result. So let me look at this. Let me look at this projection. You see, so if I take a projection like that, right? So I'm explaining that. So let's look at P, A of V, P. I compress the field by that projection. It's still a continuous field. And then I'm looking at the fibers. What are the fibers? Right, so the fibers are P of V, A of V, P of V. You see, but A of V is abstractly isomorphic to D, and P of V it's a unit. So this is isomorphic to D. So this is really a continuous field over V, where all fibers are abstractly isomorphic to D, it's a unitary field, and therefore by this theorem we'll have the field is trivial. So you see, the field, if I take a corner, a local corner, is trivial. And then by Lewis-Brown stability theorem, and then some absorption, we show that in fact A of V is isomorphic to C of V tensor D tensor the complex. Right? So in the Dixmier-Douady class, what happens if you restrict here? You get C of X, C of V. Because you have a field of complex, you compress it by a projection of rank 1. So what do you get? C of V. All right. Okay, so we have completed this first step, namely having an effective local triviality condition. And you see, let me just point out a corollary of this, okay, which is a pleasant corollary. Okay, so I assume the dimension of X is this. Okay, and A is any continuous field or separable over X with fibers. The universal UHF algebra. So, right? Then automatically A is locally trivial. So see, all fields over 5-dimensional space over the universal UHF algebras is operated. Okay, so why is that? I'll give you that event orally. We want to verify felt conditions, right? So I'm looking at one fiber, and I take any non-zero projection in the fiber. Okay? Now I can we can lift projections. We can elements which are near projections convert to projections. So this projection in a fiber can be lifted to a projection in the field which lives on some small neighborhood of the point. Because if I restrict the field to smaller and smaller neighborhoods converging to a point, the inductive limit of this system is the fiber. So we can. But that's my projection. Why? Since in continuous fields the norm is continuous, right? The norm varies continuously, and if at that point the norm of projection is 1, the norm is 1 in each fiber on a whole neighborhood. So therefore the projection is non-zero on the whole neighborhood. Okay? Does it have rank 1? Yes. What does it mean? What does it mean rank 1 here? Rank 1 means that it's invertible in Q. Any non-zero projection is invertible in Q. So see that. Felt condition in this case amounts to being non-zero. So this. Okay. So that this is okay. Now the move to the next question. Are these classifiable? We have a theory which is parallel to Dixmier-Douady, and also how do we describe the torsion elements. Okay? So we are looking at one more details. Right, this topological group. Then we know that, so this is just general homotopy theory. The bundles with fibers D tensor K, the continuous fields, right? Locally trivial vector field, continuous fields with fibers D tensor K over X. So just by homotopy theory, this is classes from X to the classifying space. So I can write this holds for any group, you know, but can we say anything interesting about this? Right, so that the theorem again was Pennig. What it happens is that this space is an infinite loop space. And moreover, see, so this is the space of loops over some other space. So this means that I have a group structure here, but the composition comes from composition of loops. But what happens, and that's part of the theorem, the corresponding H space structure, this composition that comes from loops, is compatible at the level of homotopy classes, coincides with the operation given by the tensor product. So compatible with the tensor product. So one applies, you know, this general theory of May and Graham Siegel on infinite loop machines. One constructs a permutative category, and then the classifying space is identified with this. So it's so there is a generalized homology theory which we call D star D X. Okay, such that if you look at the zero group, okay, so this is homotopy classes from X, the automorphism of beta, okay, and in fact it can be identified with this ring K0 C over X tensor D and the invertible elements in this ring. Positive. So this is. And then what is the next homology group? And this is our interest. This is precisely this. So it is isomorphic classes of bundles with fibers D tensor K over X, and the product, the operation is given by the tensor product. So what is the advantage? I mean, this is a lot of formalism of knowing that you have a homology theory. Well, first of all, this is a group, which is not at all obvious that this is a group. Like if there were continuous field with fibers strongly stable, strongly self-absorbing, why should be the tensor product? And why is this a natural structure? Oh, by the way, I should say that if you look at, this is a sister algebra, but the opposite algebra, in general, this is not fine set, unlike what happens with Dixmier-Douady. With Dixmier-Douady, it's an accident and can be traced to the following property. If you have a line bundle, the inverse with respect to the tensor product is the conjugate line bundle. That's no longer true for vector bundles of virtual rank plus minus 1. Right. And maybe I'll just say that the torsion of this, the torsion of this corresponds to bundles with fibers D tensor matrices, just like in the Serre theorem. And in fact, this our approach it gives a new proof even in the Dixmier-Douady case or Serre theorem. So it's a sister algebra approach, KK theoretical, so it has a different flavor. All right, and okay, so now computing cohomology theories is complicated. So the simplest thing, the first question is, do you know the coefficients of the theorem? So what is of the theory? So if you evaluate these cohomology groups on a point, what groups do you get? So yes, so we know the coefficients. The coefficients of the theory. So they are precisely the groups, homotopy groups of automorphism of D tensor K. So in dimension 0, this is the unit, and it's K theory. This is in dimension 0. So no UCT is assumed here. No UCT is assumed. So now, so if you know the coefficients, then up to torsion, since you have a homology theory, you know these groups up to torsions. So that they are just the usual cohomology with coefficients, those coefficients. So just to show that this is indeed effective, so if this is all, right, I'll finish with this calculation. Just to illustrate that this is efficient. So if I'm looking at bundles, you know, let me put C here to say that, to emphasize that these are arbitrary continuous fields over 5-dimensional space. And then automatically they are locally trivial. So this is a group, right? You don't expect torsion because we have the universal VHF algebra. And then the coefficients are all rational. Here it's a plus. So what you get here, so now this is computable, so it's H1, that is X, Q, plus. So these are the positive non-zero rational, plus H3, XQ, plus H5, XQ, and so on. We continue with, so this is right, this is an isomorphism of groups. And of course, if you tensor with O infinity, you have a similar calculation. And then what happens, so this is a last remark, what happens if you look at bundles with fiber the Jiangsu algebra, tensor the complex, or bundles with fibers O infinity tensor complex. So then, you know, up to torsion, in this case, you get H3 XZ plus H5 XZ plus, but here it's only up to torsion. This is always a direct sum in all cases, right? But and the last, I'll finish with the following remark, right? This Dixmier-Douady class was used in certain instances to twist K-theory for various, you know, version of twisted K-theory, and of course, one can use these higher characteristic classes, which comes from here, to give realizations of a higher twisted K-theory. And this has been worked out in a paper of by Ulrich Pennig. So anyway, if you have a field, a continuous field where the fiber is not the same, but various strongly self-absorbing algebras, after you tensor with NQ, you have a complete calculation, and therefore you have rational characteristic classes for all such fields. So you can associate here with various invariants. Thank you.
Thank you. Any questions or comments? Speaker?
So just, and if you take O2 as the coefficient,
Yes.
would you get only, you have a description, or it's all torsion things?
For O2,
Yeah.
for O2, everything is zero.
Yeah.
Right, so for O2, over a 5-dimensional space, all O2 tensor K bundled vector continuous fields are locally trivial and trivial. If you take locally trivial fields over any space with O2 tensor K, they are trivial. And in fact, that's the only Kirchberg algebra with this property. Also. Yes, so then that's.
Anyone else? Not then, let's thank the speaker again.
Thank you.